Nyla. Cheyenne, nice to see you both. Casey, welcome. How are you all today? Doing well? Good, wonderful. Lisa, good to see you. Rick, Mohammed. Just another minute or two here, and then we will get started. All right. Anybody have any questions? Okay, that's fine. In general, we like to have everybody start with their cameras on. If there's ever a reason that you can't, let me know. The idea here is the reason that we do that is just so that I can verify that you are who you say you are. Every so often, somebody from outside AIM Academy will get the link and show up in a class. Now, I've never had that happen, but I know other teachers have. So we always just want to verify, just for safety reasons, that everybody actually is a student. But I know that sometimes there are situations or locations. I had a student in a class yesterday who was in an airport. Obviously, she didn't want to leave her camera on as she was walking through the airport. So that worked out pretty well. All right. If no one has any questions, we will go ahead and begin. Maybe. Maybe we'll get there. We go. All right. All right, so physical science, of course. Look at all those words. All the words on the page there. By the end of the year, you will have encountered all of those words. Hopefully, all of that will mean something to you if it doesn't already. Pretty fascinating. Physical science is an amazing subject. All right, so yesterday, or last week, not yesterday, last week, we started learning about the periodic table. So I want to do a real quick review of what we covered last week, and then we have an activity that we're going to do together. So be sure that you have your periodic table with you. If you don't have one on paper, you can open one on another window on your computer. And I'll provide them for you to look at from time to time. But it's always more helpful if you have your own that you can look at. In fact, I think it's a good idea to have a periodic table, just have a paper one. So if you could print it, that would be good. And then, because you'll need it for a while, as we're continuing to learn about matter, of course, you could really say periodic table of the elements that make up matter, because this is what matter is all made of. All right, let's do a couple jokes first. Let's see here. All right. So this should say, how can you keep an atom from losing an electron? How can you keep, I'm going to fix it. Hold on a minute, because that's going to bother me. How can you keep an atom from losing an electron? Keep an eye on it. Ion, keep an eye. Oh, there you go, Wick. Yep, that's perfect. Perfect periodic table. All right. Why did the white bear dissolve in water? Because it was polar. It was polar, right? Polar things dissolve in water. It's a polar bear. All right. What did the girl say when her friend threw sodium and chloride at her? Anybody know what sodium and chloride are? What is sodium chloride, Wick?
Table salt?
It is just take off the table and put salt. So that's what she said. That's a salt. Salt and salt. And what is the best chemistry advice? Really, the best advice for life in general. Make like a proton and stay positive. All right, let's review the periodic table. Now remember that this square right here, we can call it a square. We can call it an element. We can call it a cell. Whatever we call it, it has some really interesting and useful information in there. It has the atomic symbol. That would be this big H. It has the name of the element, hydrogen. It has the atomic number right here, and it has the mass or the atomic weight of the element. So let's look at each of those real quickly. So the atomic number, what is that? What is the atomic number? It's 6 in carbon. What does the atomic number tell us? Quick.
The amount of protons?
Exactly. It tells us how many protons that element has. So how many protons does carbon have?
6.
Yeah, it has 6 right there. You can see the 6. Now, which two elements on the periodic table have exactly the same number of protons? It's a trick question. I don't ask very many trick questions. The answer is none of them. No two elements have the same number of protons. Because remember, if an atom loses a proton, it's not that same kind of element anymore. If it gains a proton, it becomes a different one. So in order for carbon to be carbon, it has to have 6. If it loses one, it's a different element. If it gains one or more, it's a different element. So atomic mass now. Atomic mass tells us basically we can think of it as the weight of an atom. It's a little bit different than weight because remember, you weigh a different amount no matter where you are. I mean, depending on where you are in the universe. So if you go to the moon, you're not going to weigh as much because there's not gravity. Weight has to do with gravity pulling you down toward the earth. So you're going to weigh something on the earth and you'll weigh something different if you went to the moon or Mars. So to use the word weight doesn't really apply, but on Earth it does. As long as we're talking about on Earth, we can use the words mass and weight kind of interchangeably. Basically, mass tells us how many particles something is made up of. So atomic mass tells us how many particles or what the amount of particles of that atom are. So in this case, this element is helium. It has 2 protons and its atomic mass is 4.003. Anybody remember why you can sometimes have a decimal after the number? Why it's not always exactly a whole number? That has to do with isotopes. Remember that if an element loses or gains a neutron, the neutral part of the atom, which it can do, if it either gains or loses a neutron, now it has a different weight. So that's called an isotope. And whenever you see an element that has this point something after it, that means it has isotopes. And they take the average of the number of isotopes. So we can see here that helium has 2 protons and 2 neutrons, but sometimes helium has 2 protons and only 1 neutron. That would be an isotope of helium. So we take the average of them. It is the average number of all of the isotopes that we have. Now, yeah, I did that already. Okay, so what is an ion? What do I mean by that word, ion? Guys can't make Wick do all the work today. Somebody else. All right, go ahead, Wick.
An ion is basically where an atom loses or gains an electron.
Exactly.
Because when it loses or gains an electron, it doesn't have the normal charge and it has a negative or positive charge.
Right, exactly. So by normal, what he means is neutral, no charge at all. An atom has no charge at all because it has the same number of protons and electrons. The protons are positive, the electrons are negative, they cancel each other out. So an atom is neutral, electrically neutral. When it either loses an electron or gains an electron, now it's not neutral anymore. If it gave one away, it gave away a negative, so now it's positive. If it gained one, it gained a negative, so now it's negative. But it's not called an atom anymore. It's called an ion. And remember, if it gained an electron, it is called an anion. If it lost an electron, it is called a cation. All right, so these are the 3 different main categories on the periodic table. We have metals, nonmetals, and metalloids. What color are the metals on this table? Nyla,
Blue.
they're blue. What color are the metalloids? AC,
The metalloids are green,
no,
purple, my bad.
purple. Yeah, there you go. Metalloids are in between metals and non-metals, and they have some of the characteristics of both. So they're in between. So they're this little like jagged line in between. So they're this purple color. And then of course, green would be our non-metals. So there we are. So we also on the periodic table have these columns that go up and down. Anybody remember what we call the columns on the periodic table? What?
The families?
They're called families or groups. Either of those would work. I personally like the term family because these share certain characteristics with one another. They're not identical, just like the members of your family are not identical, but you share certain characteristics with them. So the families on the periodic table they do share characteristics. So they're the ones that go up and down. What do we call the ones that go sideways? The rows on the periodic table. Cheyenne. Not hearing you, Cheyenne. Oh, there you go. Periods. Yes, they are called periods. He typed the answer there. So yeah, they're called periods on the periodic table. Just a second. There we go. So we have the groups that go up and down, or families, and then we have the periods that go across. All right. So how many groups are there? Group, family. How many are there on the periodic table? Yep, there are 18. Cheyenne's got it right. Now we can count them. If we started here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. You can see that. All right, now the rows are called periods. How many rows are there? How many periods are in the periodic table? Quick.
Wait, does the lanthanides and actinides count?
No.
Oh, then it's going to be 7.
Yeah. Why don't they count?
Well, technically they're supposed to be in the table.
That's right. They actually are part of period 6 right here and period 7. Remember, the reason that we put them there in the middle is so that our periodic table doesn't look like this. This is what it would look like if we put them in where they go. So that's really hard to see compared to the one that we were looking at before, compared to that. So we pull them out and put them down there, but they are not different rows. They are parts of period 6 and period 7. All right. Now the groups or the families, they're the ones that go up and down. They share characteristics with one another. They have similar properties with one another. The periods do not. The ones that are on the left side of the periodic table are very different than the ones that are on the right side. Just a glance at the color difference here, you can see that the non-metals are going to be very different than the metals. So as we move across the row in the periodic table, or the period in the periodic table, they're very different from one another. All right. So what is this first group or first family called? AC?
The hydrogen group.
Well, hydrogen is all by itself. Hydrogen is not in a group. It's all when a periodic table has colors, it's almost always a different color because it's all by itself. It has very unique characteristics. So we give it its own space. So basically we're talking about these red ones right here. What are they called? AC.
They're alkali metals in a lithium group.
They are alkali metals right there. We don't really say lithium group. You may see that written down somewhere, but the better way to refer them to is alkali metals. The only ones that are named after their group are these 4 that are named after the one at the top, are these 4 here. All right, so the red ones are alkali metals. What are the ones in group or family 2 called? Look.
Alkaline earth metals.
Yep, they are called alkaline earth metals. Absolutely. All right, now, The ones in the middle, right here, these are called transition metals, and we put them aside for a minute. We don't talk about them quite yet because they're a little bit more complicated. We talk about the easier ones first. So what are the ones in group 13 called? Remember I said they're named, these first four are named after the element at the top. Not quite halogens, not yet. We're looking at this one right here. So what is this element? Nyla?
It's the boron family.
Yep, it is the boron family. Very good. Then what about the next one? Wick?
Carbon family, and aren't the bottom three the poor metals?
Aren't the bottom three what?
The poor metals?
Poor metals? I don't know what you mean by poor.
Oh, for some reason my table says that they're aluminum, gallium, indium, tin, and all of the other ones that are below the metalloids, colored in dark green,
Yeah.
are the poor metals.
P-O-O-R?
Yeah.
That's funny. I've never heard that term before. I'll
Huh.
have to look that one up. I don't know, as opposed to the rich metals on this side. I don't know. Good question. I'll look and see what I can find with that. All right, so this is the boron group all the way down. This is the carbon group. And yeah, notice that one of them is a non-metal. Two of them are metalloids, and then these three are going to be metals. But they do still share some characteristics with one another. Far fewer than these do. These all share a lot of characteristics. So the farther over we go, the less characteristics they're going to share with one another. All right, what's the next group called? Group 15. Quick.
The nitrogen group?
That is the nitrogen group. And then this one? Nyla.
The oxygen group.
The oxygen group. Excellent. Now this last one here, we don't call this the fluorine group. What do we call that next to the last row? I'm sorry, next to the last group. AC.
Is it the halogens?
Yep, those are the halogens. Very good. And then finally, what do we call these beautiful purple ones? They're very royal. Wick.
The noble
The
gases?
noble gases. I like when they put it in purple on the periodic table because you know it looks very regal, like a king. They're noble. They're the noble gases. And then of course we have these two at the bottom here. We have the lanthanide series and the actinide series. So we didn't really talk too much about them last week. Just remember that they are supposed to go. A lot of times you'll see these two will be blank on the periodic table. That's because these all go in there so that it ends up looking like that if we put the table together. But we do it this way to save space. Now, all these lanthanide elements, all of them except for promethium, this one, are naturally occurring. And we can find them in some mineral deposits on Earth. 5 of the elements in the actinide series are naturally occurring. They're these ones right here. Those are naturally occurring. 5 of the isotopes of the other ones are sometimes made when uranium breaks down, when it decays. The rest of them have been made in the laboratory. All right, so there's our review of our periodic table. We also have to talk about these valence electrons. Quick.
Yeah, so my periodic table over here, it's showing, so it says it's color coded and it says which one's which. Don't think you can.
Yeah, it's too blurry when you hold it up close.
Okay, let me off my blur. I think, oopsies. There, it should work now. Yeah, so it's red under the metalloids.
Yeah.
And it says that it's poor metals.
Okay, I'll look that up. All right, so let's get back to the valence electrons. They are really important. They're the ones on the very outside of an atom. And it makes sense if you think about it. What is going to come into contact with other things first? The things deep inside the nucleus or the things on the outside? It's going to be the things on the outside. That's what's going to come into contact with another element first. Like you can see it here. The nuclei never come into contact with each other. It's the outer valence electrons that do. So they determine whether or not an element is reactive. So what do we mean when we say reactive? What makes an element reactive or not? AC.
An element would be reactive when it had a high number of valence electrons or a really low number, like 7 or 1.
Yeah, exactly. So really high up to 7, basically. If it has less than 7, it's going to be reactive. Because remember, a complete valence electron level has 8. So when an element has an incomplete valence electron level, when it has fewer than 8, it's reactive. It wants to react. Again, we've got a couple that are exceptions, hydrogen and helium. Those are exceptions. Wick.
Yeah, so I was also kind of confused. On the last slide, why do valence electrons actually want to bind? Because don't the negative electrons oppose from binding?
Well, they don't really bind with each other. It's not like one electron binds with another. They bind with the shell. You're getting a little beyond the scope of our course right now. We'll learn about electrons a little bit more. We'll learn about how they move. They don't move in circles like this. Let me get the picture of that. They don't move, look like they're round like the sometimes you have to learn something a little bit wrong in order to understand it before you can get to the more complex. Like you guys didn't start out with algebra when you were in kindergarten. You started out with just learning your numbers and then adding them together. You have to work your way up. The same is true here. We tend to describe an atom as being flat and being almost like an orbit going around the sun. They're not really like that. They move in a very complex pattern. They want their outermost complex pattern to be full. So it isn't that they stick to other electrons, it's that they go into the other electron's outermost shell. Does that make sense? See these two that are paired, that are, let me see if I can, I don't know if I can pause that. No, I can't. So when they're by themselves, they don't stick to each other. They form two there. It's not the greatest picture. I think I might have a little better picture coming up. All right, bear with me for a minute. Maybe I'll answer your question. So there's a certain number of electrons that atoms want to have in their outer energy level. You got it, Cheyenne. They want to have 8. All atoms, except for hydrogen, want to have 8 electrons in their outermost energy level. Now, helium also, that's another one that is an exception because it's got a full outer shell. It's only got the innermost shell that holds 2. Wick.
Is helium a noble gas?
Yes. Yep. Helium is very, very stable. All right. Now, what is the rule that tells us that all atoms want 8? Wick.
The octet rule?
Yep, it is called the octet rule. You can sum the octet rule up with 3 words. I want 8. Electrons, our atoms want to have 8 electrons in their outer energy level. So they're going to keep bonding until they have 8. Now, atoms with not very many electrons are going to lose them because it takes less energy to lose electrons than it does to gain like a lot of them. It takes less energy to lose 2 than it does to gain 6. So they're going to lose those 2. Atoms that have 6 or 7 or 8 electrons in the outside, they're going to gain more because it takes less energy to gain 2 than it does to get rid of 6. So it all depends on where they are on the periodic table. And we can know how many valence electrons they have by looking at the periodic table. Wick.
Yeah, I'm kind of confused. When it has 4 electrons, is there a specific direction that it has to go, or does it like depend on what it binds to?
It depends on what it binds to. So those would be the ones here in the middle. Remember I said that these transition metals right here are a little more complex, so we put them aside until later. We won't talk about them right now. We'll get to them later because the way they bind is complex. So we're really only working on these 2 columns and then these 6 columns right here. The 6 families that are over on the right, the 2 that are over on the left. Yeah, that's a very good question. And again, just hold that, we'll get there. All right, so atoms on the left side don't have very many valence electrons. All the ones that are in column 1, in the group 1, have only 1. All the ones in group 2 have 2. These, they can have anywhere between 3 and 12. The ones that are here in group 13 all have 3 and 4 and 5 and 6 and 7 and 8, except for helium. The helium only has 1, but helium is, it's a noble gas. It only has it has 2 electrons. It doesn't have 8, but its outer shell is full. Its outer shell only needs 2, so it's happy. It's happy all by itself. Now, atoms that have 6 or 7 are going to pick up more electrons. They're going to gain them. So if we know where something is on the periodic table, we know how many valence electrons it has. If we know how many valence electrons it has, we know if it wants to gain or lose during bonding. AC.
Can 3 atoms or elements bond together, like one that has 4 valence electrons, one that has like 3 and 1?
Yep. If they didn't, if they weren't able to bond with multiple different other atoms, we wouldn't have nearly as much variety as we have of compounds. Remember, 2 atoms that bond together are compounds, and the world is made up of compounds and things that are made of those compounds. So yeah, there's a lot of bonding that can happen. Yep, great question. All right, so let's see here. So here's a good example. Here you have, I don't know why some of these go so fast through it. Here you have 1 unhappy sodium atom. Sad face, because how many valence electrons does sodium have? 1. It's not happy. It wants 8. Here you have a chlorine atom, and the chlorine atom is also unhappy. It has 7, but it wants 8. So if I have 1 apple and you have 7 apples, and I don't want 1, I'd rather have either 8 or 0. 1 just makes me mad. I want either 8 or none. If I've got 1, it's easier for me to give you my 1, takes less energy to hand the 1 over to you, and now we're both happy. You have 8, I have 0, we're both happy. That happens with chlorine too. Sodium will lose an electron. Chlorine will gain an electron. See sodium losing it? It's going over there. It's not bonding to another electron. It's going into that valence shell on the outside. Yeah, you're right, AC. What we end up with is sodium chloride. Now we have a happy sodium, we have a happy chloride, and we have happy people because we have something to put on our French fries. We have salt, right? All right, let's play a little game, or do an activity rather. We're going to build an alien periodic table. So we have to imagine that inhabitants of another planet have sent a message to Earth. That message has information about 30 different elements, and they want to enter into a trade agreement with us. So they want to buy some elements from us and sell some elements to us. But we have some problems. There are 2 big problems that we have. The first problem is they only have 30 elements on their home planet. This is how many they have right here. We'll look at ours. They are completely missing all the ones in the middle. So let's take them out. They're completely missing all the ones that I just deleted. So here are the elements that they have. That's problem number 1. The second problem is that they don't have the same name. The message uses different names and symbols for their elements than those that we have here on Earth. They use names like Apstrom and Zapper and Bomble and Logon and Vulcania. All right, so we have to figure out, our job here is to discover which of the elements on their periodic table those names represent, so we can give them what they want when they place an order for us. So we're going to use some clues and place the elements in their proper position in this simple periodic table. All right, now here's clue number 1. The noble gases are Bombol, Wobble, Gyptum, and Logon. B-O-W-O-J and L. Among these noble gases, Wobble has the greatest atomic mass, and Bombol has the least. Logon is lighter than Gyptum. All right, so what's going to go up here on the top? Which of these 4 noble gases goes on the top? Quick.
I'm kind of confused because they only have 4 noble gases.
Right, right. They don't have the whole periodic table.
Wait,
That's
so
all they have on their planet. This is another planet and they're weird. They don't have all the elements.
okay.
Because you know why, Wick? It would take us about a week if we had to do this for the whole periodic table. So we have a simplified periodic table that we're going to make. Okay, so AC says Bombol. Anybody disagree? He is correct. It is Bombol that goes on the top. All right, what goes on the bottom? What goes right down here? Which one has the great, remember, mass increases as you go down the periodic table. Nyla.
Womble.
Yep, absolutely. All right, now we just got the 2 in the middle. Logon is lighter than Gyptum. Lighter meaning it has a smaller atomic mass number. So which one is going to go right here? Yep, you got it, Cheyenne. Logon and then Gyptum is going to go right there. All right, you get the idea. You know what we're doing now. All right, we're going to leave those in place and we will go to the next one. The most reactive group of metals are Extalt, Biu, Chow, and Quoxel. All right, which group on our periodic table has the most reactive elements in it?
The first one?
It's going to be the first one. What's the first one called? Go ahead, Wick.
Alkali metals?
Alkali metals, yes. Group 1, alkali metals, family 1, those are the most reactive of all the elements on the periodic table. Remember, they've only got 1 electron in their outer valence shell. So they just want to get rid of it as quickly as they can. That's what we mean by reactive. They react very quickly to get rid of that 1. So now their most reactive group of metals are these 4, Extalt, Biu, Chow, and Quoxel. And notice that we have this one set aside. It's not part of that. Okay, so we're looking at these 4 right here. Of these metals, Chow has the lowest atomic mass. Quoxel is in the same period as Wobble. Period, remember, goes across. There's Wobble, the same period. Biu has a greater atomic mass than Chow, but less than Extalt. All right, what goes here? Anybody who hasn't contributed yet want to? Wick.
Chow.
Yep, Chow. Chow has the lowest atomic mass of these metals. So it's going to go right there. All right, then what where is Quoxel going to go? Tell me group and period. Wick.
Group 1, period 4.
Group 1, period 4, right there. Group 1, period 4. All right, what about Biu? Go ahead, Wick.
Biu is group 1, period 3.
Yep, group 1, period 3, because Biu has a greater atomic mass than Chow, but less than Extalt. So greater atomic mass than Chow means it's going to go here, but less than Extalt means we got to have a place for something heavier. So that's going to be the X for Extalt right there. All right, let's keep going. We got both sides now. We have our very reactive and our non-reactive. So our noble gases are here. Our very reactive elements are over here. Let's go to the next group now. Apstrum, Vulcania, and Krat are non-metals whose atoms typically gain or share one electron. Okay, since they're non-metals, which side of the table are they going to be on, the right or the left? Where do non-metals go? AC.
On the right.
They're going to be on the right. Yep, absolutely. All right, so they're going to be on the right. They typically gain or share one electron. So which group are they in? Quick.
Group 17?
They're going to be in group 17. Absolutely. All right. Apstrom has the lowest atomic weight of these three elements. Vulcania is in the same period as Quaxel and Wobble. All right, so where should Apstrom go? Go ahead, Wick.
Apstrom should go in group 2. Group 2, wait.
Group 2 is way over here.
Oh, group 17 period 2.
Yeah, group 17, period 2. Very good. All right, now where does Vulcania go? AC.
Group 17, period 4.
17, period 4. And that leaves a space right there for Krat. All right, we're nearing half done. All right, remember the metalloids are the ones that look like steps. So I have them boxed right here. The red boxes are going to be the metalloids. So the metalloids are Ernst, Hi-Ho, Tereblum, and Sisyphus. Sisyphus is the metalloid with the greatest atomic mass. So where is Sisyphus going to go? It's one of those red boxes. It's a metalloid and it has the greatest atomic mass. Quick.
Wait just a sec. My periodic table isn't working. I'm not sure which one is more heavy. Is
So
it?
remember when we're looking at, let me go back here to a real periodic table. Where is there one? Here we go, the periodic table. Remember, atomic weight increases as you go across and down. So this is going to be the lightest one. And way down here, 118 is going to be the heaviest one. So as we go across to the right and down, they're going to get heavier. All right, so back to our periodic table here. There we go. Which one is going to have the greatest atomic mass?
Arsenic. Or, well, not arsenic.
No, don't do that yet. We'll get to that. We'll match them. Right now, we're just trying to figure out where they go.
Sisyphus.
Yep. Which is where is it going to go on the periodic table?
Group 4. No, wait. Group 15, period 4.
Good, very good. Yeah, those terms are confusing, aren't they? Groups and families are up and down. Periods go across. All right. Now, Ernst is the metalloid with the lowest atomic mass. Where does Ernst go? AC.
Group 13, period 2.
Excellent. Very good. Hi-Ho and Tereblum are in group 14. We'll find group 14. Tereblum has more protons than Hi-Ho. So where is Hi-Ho going to go? Go ahead, AC.
It's going to be group 14, period 3.
Excellent. Excellent. And then we know that Tereblum is in the same group, so it goes right there. Now, Yazur is in the same group as Ernst and the same period as Hi-Ho. It touches the zigzag line, but it's a metal, not a metalloid. So we don't have it in a box. So it's in the same group as Ernst and the same period as Hi-Ho. Where's Yazur going to go? AC.
Group 13, period 3.
Excellent. Very good. All right, we are about half done. Going faster now that we know what we're doing. The lightest of all elements is called Pst. The heaviest element in the group of 30 is El Dorado. So where does Pst go? Lick.
Where helium should go?
Not helium. We've already got helium right here.
I mean, hydrogen.
Yeah, it goes where hydrogen should go, right there. 1-1, period 1, group 1, period 1. What about El Dorado? Where should that go? AC.
Group 14, period 5.
Excellent. Is the heaviest one on their periodic table. Very good. Very good. All right. Now, the element doggone has only 4 protons in its atoms. Where does doggone go? Wick.
Group 2, period 2, where beryllium would go.
Hold on, Wick. We'll get there. We'll match them up. I promise. I promise. All right. Now, floxate is important in the chemistry of life. It forms compounds made of long chains of atoms. Floxate has 1 more proton than Ernst. Where does floxate go? Find Ernst. Floxate has 1 more proton. All right, somebody else besides AC and Wick. You guys are making them carry the load today. 2-14. 2. I don't really see a 14. Oh, usually we do the group first. So yeah, 14-2. Very good. Now, very good, Cheyenne, noting that was 2. It looks like a 1 because it's at the top, but remember, our periods start at the top with just hydrogen, helium. Theirs starts with just and bow. Forget what bow stands for, but Bombal. That's what it is, Bombal. All right, so we got floxate. Sorry, we've got floxate in there now. All right, next, rat trap and duodir are metals in the 4th period. So where's the 4th period? 1, 2, 3, 4. They're metals, so they're going to be on the left side of the periodic table. But rat trap is less reactive than duodir. So what goes here? Wick.
Rat trap.
Yep, rat trap goes there.
I thought of rat trap as rat trap.
It's rat trap. And then duodir goes right there because they're both in the 4th period. All right, nearly done. Magnificon, Goldie, and Sisyphus are all members of group 15. Let's find group 15. Here it is. These are all, so Magnificon and Goldie go in here. Goldie has fewer protons than Magnificon. Where does Magnificon go? Wick.
It goes at 15,3.
Yep, very good. 15-3. Group 15, period 3. What about Goldie then? It goes in the last space right there. All right, now we have Earp, Oz, and Nuyut. They all gain 2 electrons when they react. Since they gain 2, are they going to go on the right side or the left side of the periodic table? AC.
The right side, and they have 6 protons.
Yep, very good. Now, what group are they in? Wick?
Group 14.
Not 14. 14's full. AC?
Group 16.
Yeah, they're going to go in
Or
group
they
6.
have 2 less.
Yep. All right, now, Nuyut is the lightest of the 3 elements. So where's Nuyut going to go? Going to go in group 16, which period? AC?
Group 16, period 2.
That's it. Very good. Now, Nuyut is found as a diatomic molecule, and it has the same properties as a gas found in Earth's atmosphere. So anybody remember what group is 16 on our periodic table? What do we call that group? Wick?
The oxygen group.
The oxygen group. So that is oxygen on our periodic table, which again, we'll get there. We'll match them all up here in just a second. But yeah, it is found diatomic. Oxygen is only ever found binded to another oxygen naturally on Earth. And we can separate them. Remember we learned last week, we talked about how we can run electricity through them and separate those two, or we can separate them with high heat. But as soon as they find each other, they bond right back together again because they want to be an O2 molecule, not just an O. All right, last we have Oz. Oz has a lower atomic number than ERP. So what's going to go right here? Quick.
Oz.
Oz has a lower atomic number than ERP. Remember, atomic number goes up as you go down the table. AC.
And group 16, period 3 would be ERP, I think.
Now let's look again. Oz has a lower atomic number. That means it's lighter. So it's going to be higher on the periodic table. So ERP has a bigger atomic number. So it's going to go here. ERP is going to go here and Oz is going to go here. I know sometimes this can get to be a little bit confusing. All right, we are almost done. The element anatom has atoms with a total of 49 electrons. It is the second largest element on the table. Where should anatom go? AC?
Group 13, period 5.
That's it, group 13, period 5. Zapper and pi lose two electrons when they react. Pi has more protons than Zapper. So what goes right here? Quick. Zapper, yep. And then last but not least, we have pi. And with that, our table is complete, but our job is not done. We still have to match them up with our elements. So we know what their elements are. We know what our elements are. We just have to match them up. So what element is quick?
Hydrogen.
Hydrogen. Which one is Bumble? AC.
Helium.
Helium. What about Chow? Nyla.
Lithium.
Lithium. Doggone. All right, why don't we all holler them out together so we move through this a little more quickly. Just, you don't have to just leave your microphone on for a minute and we'll holler them out together. So doggone is
Beryllium.
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 very good. What about Ernst?
Boron.
Boron. What about Fluxit?
Carbon.
Carbon.
What about Goldie?
Nitrogen.
Nitrogen.
Nitrogen. Nuyut?
Oxygen.
Oxygen.
Oxygen. Abstrom.
Fluorine.
Fluorine.
Green. Logon.
Neon.
Neon.
On one of those non-reactive noble gases. All right, now to the other side of the table again. Bayou.
Sodium.
Sodium.
Sodium. Zapper.
Magnesium.
Magnesium. Yazer.
Aluminum.
Aluminum. Hi-ho.
Silicon.
Silicon. The second most common element on Earth's crust is silicon. Magnificon.
Phosphorus.
Phosphorus.
And then Oz.
Sulfur.
Silicon.
Sulfur. Krat.
Chlorine.
Chlorine. Gyptum.
Argon.
Argon.
Argon. Quaxel.
Potassium.
Potassium. Doadir.
Calcium.
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 Calcium. Rat trap.
Gallium.
Gallium.
Gallium. Terriblum.
Germanium.
Arsenic.
Germanium. Yeah, germanium. Sisyphus.
Arsenic.
Arsenic.
Arsenic. Erp.
Selenium.
Selenium.
Volcania.
Bromine.
Fluorine.
Bromine. Wobble.
Krypton.
Krypton.
Krypton. Extalt.
Radium.
Radium.
It's rubidium, actually. It's kind of hard
Rubidium.
to read on that table. Rubidium. And then pi.
Strontium.
Strontium. Sorry, it's a little bit blurry. Strontium. All right, anatom.
Indium.
Indium. And then El Dorado.
Tin.
Tin.
All right, excellent job. Now we can trade with the aliens, and hopefully you learned a little bit more about the periodic table in doing that. All right, so let's just do a real quick review here. Now remember that we have hydrogen all by itself up here. And then we have the alkali metal family. That is period 1. Period 2 are the alkali earth metals, sometimes called alkaline earth metals. Both work. Then we've got all these little more complex transition metals in the middle. Then this would be boron, carbon, nitrogen, and oxygen, because the top element in these families is boron, carbon, nitrogen, and oxygen. This one is called the halogen family, and these are the noble gases. Excellent. All right, so in your lesson, in one of your lessons, there's a video of a song that covers all the elements on the periodic table. But Daniel Radcliffe, who is the actor who plays Harry Potter, he actually was on a talk show a few years ago, and he sang another version of the periodic table that I thought you might enjoy watching. And he sings really fast, but it's kind of fun. So let's watch this.
There's antimony, arsenic, aluminum, selenium, and hydrogen, and oxygen, and nitrogen, and uranium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and anthium, and osmium, and acetine, and radium, and golden, protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, and terbium, actinium, rubidium, and boron, gadolinium, and niobium, and iridium, and strontium, and silicon, silver, and samarium, bismuth, bromine, lithium, beryllium, and barium. Let's start the next verse. There's holmium, and helium. There's holmium and helium and hafnium and erbium, phosphorus and francine and fluorine and terbium, and manganese and mercury, molybdenum, magnesium, dysprosium and scandium and cerium and cesium. There's lead, praseodymium, platinum, plutonium, palladium, promethium, potassium, polonium, and tantalum, technetium, titanium, tellurium, and cadmium, and calcium, chromium, and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, arseninium, nobelium, and argon, radon, neon, and argon. Hold on, quiet. There's sulfur, californium, and fermium, berkelium, and also mendelevium, arseninium, nobelium, and argon, radon, neon, krypton, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. Now,
All right, how's that for a challenge? All right, so if you guys want some extra credit, if you learn any version of the periodic table of elements song and sing it in one of our live classes, you will get 25 extra credit points. And you get serious bragging rights, right? So if you learn it, send me a Canvas inbox message letting me know that you want to sing it in class, and I will give you the time to do that. All right. There is another table too. Last week I sent you an interactive periodic table, and I thought you might like to see a different one that's kind of cool. It has some different stuff in it. So let me load that, bring that over so you can see it. This is what it looks like. So this is called Blue Coral periodic table. Just type Blue Coral periodic table into, I'll send you a message letting you know that that's what it is. So let's click on one of these. Let's click on carbon. So then it shows carbon up here. It also shows us a lot of information here. It'll tell us what state of matter carbon is in. So carbon is, look over here to the key, a solid at room temperature. These are all going to be at room temperature. Outer orbital, the outer orbital of carbon is going to be what we call the p orbital. We'll learn all about these. That's where I'm talking about the kind of crazy shapes that they move around in. It's a p orbital. Electronegativity, it has a negativity of 2.0 to 2.9. It has a melting point of, let's look there and see the kind of pink color. It's going to be, well, pink isn't really even on there. Well, that's confusing. All right, let's look at one that is on there. There we go. So boron has a melting point of 2 and above, 2 per 1,000 degrees Celsius, values per 1,000. So you can do that with all these different elements. And I just think it's interesting to look at different periodic tables. All right, anybody have any questions? All right, great job putting together the periodic table today. All right, have a good week, everybody. I'll see you next time.
Thank you.
Bye.
Goodbye.
Thanks.
Thank you.
You.